How to mess with chemical equilibrium. This is Le Chatelier's principle, based on the work of Henry Louis Le Chatelier, who died in 1936. This is screencast 14.5. We will learn a good analogy for predicting equilibrium changes. What happens if you add, for example, reactant? Will it tend to push the equilibrium forward or backward? How can you make a reaction go forward or backward by working with concentration or temperature or pressure? And can you think of a way that you can make it so a reaction can only move forward? This is screencast 14.5, and let's begin. Okay, Henri Le Chatelier. He stated, and we're going to make a heavy sort of translation here to try to make it more understandable to the average student. Equilibrium can be adjusted by changing concentration, temperature, or pressure. Those are the three things that he focused on for ways to adjust equilibrium. And they're things that people do out in the world all the time, and they tend to work pretty well. Let's teach this by example. Imagine A and B is turning into C. It's a little bit endothermic, so it needs a little bit of heat to proceed, and it's not a one-to-one ratio of reactants. Let's imagine what would happen if we added some reactant, A or B. What should that do? That should push the reaction forward, most people would just think intuitively, and they'd be right. A great analogy is a wood fire. It'd be like adding wood to a fire, or maybe adding oxygen to a fire. You're stoking it. If you add product, that's going to push the equilibrium in the reverse direction. It's a bad idea. If you're quenching the fire, if you heat it up, it will make it go faster, but that's not what we're asking. We're asking, will it push it forward or backward? And the general rule is, if it needs heat, it will help the equilibrium. This is an endothermic reaction. It does need heat. So it should move it forward. Reason? It's endothermic. It needs it. What about pressurizing it? The general rule here is the equilibrium will favor the fewer number of moles. And we've got 1 plus 3 of the 4 moles here turning into 1 there. So this should say 1 is less than 4, but it says 1 less than 3. You get the idea. The product will have fewer moles, so pressurizing it will push the reaction forward. Many more examples. We're oxidizing nitrogen monoxide, and once again it's an endothermic process. Let's think of all sorts of changes. Let's add some reactant. That's going to move it forward. That's the principle. Add some product, that'll move it backwards. Add some oxygen, that's another reactant that pushes the reaction forward. We are stoking the fire. Removing a reactant. Well, the easy thing to do is give the opposite answer of what's adding it. Excuse me. It should remove it backwards. Move it backwards. Let's remove some product. Not only a good idea in that it can move it forward, but in the last slide, and I hope you're thinking about this, this is a particularly good idea. Remove oxygen. Well, opposite of adding it. Move it backwards. Increase the pressure. We are going from, let's see, 3, 2 plus 1, to 2. Fewer moles is in the forward direction. It should help. Increase the temperature. Does it need heat? You bet it does. It's a positive number, meaning it's endothermic. It needs heat. That'll help. And the opposite of increasing is decreasing, so backward. The opposite of decreasing the temperature was increasing there. Let's see, so that should move it backwards. And those are several applications of Le Chatelier's principle, and let's move to the punchline. The best way to drive a reaction to completion. Do you remember that removing the product thing? If you can remove the product as formed, well, how can the reaction possibly go backwards? The product is gone. There's no way that mechanism can occur. So if you remove the product as formed, that's wonderful. A couple easy ways to do that. One, have it be a gas bubbling out of a mixture, like an aqueous mixture. Wonderful, it's gone, unless it's dissolved in a liquid. You don't want that, but let's assume you can get it all out there. How about making it precipitate, crash out of solution? It's gone there. That's another way to do it. What if it has a boiling point lower than the solvent of a aqueous or a solvent-based mixture? Then you could just distill it out. And there's other cute ways you can do that. But if you remove the product as it's formed, you can get great yields for a chemical reaction. That ends Unit 14.